Working? Are we live? Maybe. Yeah, I think I am. Okay, cool. So, what am I doing? So, I was going through programming language foundations in Agda. This is what you're seeing right now. Agda programming language foundations. So the idea, I guess, is that you learn programming with this book, or maybe we should actually read the cover. I think quite well written. Introduction to Programming Language Theory. All right. So you don't learn programming with this book, but you learn how to write programming languages within Agda, which matches my experience with how I saw people use Agda, because what they are doing is design type systems, for example. And yeah, so what did I do before? So I already installed Agda on this system, which was an incredibly pain in the ass to do, but here it is, reproducible on Nixos. We have on NixOS, we have Agda, and this is in my Emacs daemon mode that's completely managed with Nix. The packages are managed with Nix. So great, we got it to work. It compiles stuff, so I can do Ctrl+C, Ctrl+L, which loads things. I think we will get compile errors if I fuck up. Yes. So I fucked up there, and it showed it's broken. That's great. What we want. We want our little tier improver on our side. Do it again. I don't know how you reload. Ctrl+B, Ctrl+L. There we go. So yeah, that's reloading. Cool. So what did I do then? I went on doing the first exercise. So let's just read along. So this is the introduction. The night sky holds more stars than I can count, though fewer than 5,000 are visible to the naked eye. How did you know if you didn't count? The observable universe contains about 76 billion stars, and this is an estimation, definitely. It's kind of interesting how you do that stuff, because you just like take a square in the sky and then, you know, count the stars in there, and then you just like map out where all over the sky, see how big it is, right? That's how you do the estimation, multiply by what's in that. So that's what I did, and I came on the number billion. Still, like even if you do like 1 square centimeter of a night sky, see, there will be billions of stars, so I don't know how to count that. I would like to have a reference on that, but whatever. The number of stars is finite, while natural numbers are infinite. Count all the stars and you will still have as many natural numbers left over as started with. It's like rules of infinites. Isn't, you know, infinite plus 1 is equal to infinite gross. Okay, cool. I guess that's like a little mind-blowing introduction. Everyone is familiar with natural numbers, blah blah blah. We write this n thing, which stands for natural numbers, and if you zoom in a little, I don't know if you can see it on screen, but it is like n with a white space in between, like the special symbol for natural numbers. Oh, and by the way, I got it in Emacs. I just copy pasted it. So I just copy pasted this code, and then I just used my Vim bindings to copy paste it for 7. The exercise we'll see in a bit. And so on. We write n for type natural numbers. Say that blah 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 a set of values of type n, indicating that writing 0 is n, 1 is n, and so on. But it's just Haskell typing, right? Like n is natural numbers, and we give it a type. 1 is a type, blah, blah. Oh, and interesting fun fact, you would call this constructible in hot, but we're not doing hot, we're doing normal Agda. So hot will come later. The set of natural numbers is infinite, yet we can write down its definition in just a few lines. This definition of power inference rule. Here's the set definition in Agda. So presume this is kind of like I would actually logic, probably looks more like logic. It could also be type theory, I don't know. That's what they give us, inference rule, without explaining what it is. Whatever. Oh, I wonder if the notification board it didn't say. Okay, cool. We'll just continue. That's how you jump into a stream, like halfway through anyway. So one wonders how useful it is to give an introduction. But that's what we're doing. Well, not really. I'm just going over what I already went for. Oh, I pushed it out. I was looking at my what I can see on camera. There's a bit of lag here. N is the name of a data type we are defining, and 0 suck are the constructors. Both definitions above tells 2 things. Base case 0 is natural number, inductive case m is natural number, blah blah blah. For these rules these two rules give only ways further. These two rules give the only ways of creating natural numbers. Hence, the possible natural numbers are 0, suck 0, blah blah blah. You write 0 as a shorthand for 0 and 1 as a shorthand for suck 0. The successor of 0, That is the natural that comes after 0, and 2 shortened for suc0, which is the same as suc1. So, and then the exercise comes, you know, right, a succession of 7, which is what I did here. It's like, you know, just count the sucs, I guess. This is 1, 2, 3, just what I did. Okay, and then we enter this little paragraph, which is basically going over in great detail over what these judgment rules are. So this is the judgment, or the inference rules are. This is the judgment, this is the conclusion. Yeah, and so that they explain like, oh, 0 has no judgment, so it's always true. And yeah, so you always can say the conclusion. And for 2, you need to have the judgment M to be natural, have conclusion be true. Yes, and a conclusion also a natural. So I don't really know what they do. They're just explaining what they are. They don't really explain what they do, but maybe that comes on later. So here they go over Agda rules again. I don't think this is really that interesting because it's just the same as in Haskell, pretty much. You know, it's got its yeah. So maybe we can read through it, but let's unpack the Agda definition. Keyword data tells us that it's an inductive definition. That is, we are defining a data type for vectors. The phrase tells us that M is the name of the new data type and that it is a set, which is the way in Agda of saying that it is a type. That's an important thing, by the way, later on, because this assumes types are sets, but there is another theory called homotopy type theory, which says types are not sets, but types are what are types? Types are equal to each other up to isomorphism. So it basically leverages it uses a different base axiom. So sets, that theory uses one axiom, find truth, and hot uses a different one. But it's not important for us right now, so I'll skip over that as well. Tells us that type. So it, like this Agda way saying it's a type, which may or may not be completely true. I don't know, maybe I'm misunderstanding, but I think that's what they're doing with hot. Hot. Okay, so which is set, which Agda way of saying it's type based around set theory. Okay, cool. The keyword where separates the declaration of the data type from the declaration of the constructor. Its constructor is declared on a separate line, which is to yeah, so it's got it. They tell us that 0 is a natural number, subject number. You have to notice that don't appear on your keyboard. Okay, Unicode, whatever. Yeah, like I already read it before, so it's this is new to me. So let's take more time for this. So base case 0 is natural. Oh, we're still on this. Inductive case, if M is natural, then suc is also a natural number. Hold on. The second line defines natural numbers in terms of natural. Wait, what? Second line defines natural numbers in terms of natural numbers. How can it possibly be allowed? Isn't this useless definition of Brex? No, you get your base case. It's fine. In fact, it is possible to assign your definition meaning without resorting intermediate singularities. Furthermore, we can do so while working with finite sets and never referring to infinite sets of natural numbers. We will think it of a creation story. To start with, we need to know about no natural numbers at all. In the beginning, there are no natural numbers. Now we apply the rules to all the natural numbers we know about. The base case tells us that 0 is a natural number, so we add the set of known natural numbers. The inductive case tells us that if M is a natural number, before today, then suc M is also a natural number. Then we repeat the process. The process continues. The nth day will be nth day. Okay. A process like this is called inductive. We start with nothing and we build up the potential infinite. Yeah, so it's basically recursion, right? In programming, we call this recursion. So you have a base case and you have the recursive step. This is what they call a logic induction. And these are the same things, by the way. So it took me a while to connect these things when I was in grad school, but yes, these are the same things. I mean, I can see why I make a big deal of it. It's difficult to understand if you've never seen it before. Unfortunately, I have. So the rule definition is called base case because it induces natural numbers. Even when we know oh, I should change the title, by the way. Learning to program in Agda. How pointed. Sucky, indeed. Okay, cool. Oh, I wonder who will help me. See, now you have a reason to move to Sweden. Agda is Swedish. That's true. It's invented by some Swedish university, I believe. But I'm afraid if I meet these people in person, I will beat them up. Because they've been so trashy to me. Well, one of them has been. Not all of them. Most of them have been nice. Yeah, kick their teeth in. I mean, they will fall on a doorknob. The Quick Check boys work at Chalmers. Oh, really? Quick Check boys. Quick Check is quite old, though. You should write a blog post on how to Quick Check. There's like so many interesting things about it. But let's not get distracted and let's learn about philosophy and history in Agda. A philosopher might observe that our wait, did I read this? I probably did. Whatever. Yeah, Brexit. Okay. A philosopher might observe a reference to the first day, second day, and so on implicitly involves an understanding of natural numbers. In this sense, our definition might indeed be regarded as in some sense circular. But we need not let this disturb us. Everyone possesses a good informational understanding of natural numbers. So this is like this is an argument by intimidation, basically. Everyone knows this. This is common knowledge. So just don't worry about it. Which we may take as our foundation for their formal description. So this is actually this is fallacy. Congratulations. Can't remember his name. John Hughes. Quick check. I'm gonna do some things to Quick Check soon. Yeah, it's gonna be kind of ugly, but useful. I'm not ready to Quick Check. I'm gonna do things with Quick Check to other things. But yeah, we'll see about that. I hope it works. It will be kind of a cool trick. While the natural numbers have been understood for as long as people can count, the inductive definition new place. What do you mean new place? While the natural numbers have been understood for as long as people can count, the inductive definition of natural numbers is relatively recent. It can be tracked back to Ricard Dedekin's paper. Was sind und was sollen die Zahlen? What are and what should be the numbers? Published in 1888. And Giuseppe Piano's book, Arithmetic Principia Nova Methodia, Principles presented by a new method, published the following year. Yeah, that's funny. They call it the piano construct and not the Dedekin's construct. The regular piano construction will do. No more talk, more read. No, talk. I need regular breaks from this book, otherwise I'll get too angry. That is not true. This book is not that infuriating. It's just a lot of words all over the place. That's fine. The homotopy type theory book was kind of frustrating because, you know, I read the word homotopy type theory and then I, you know, kind of tried to figure out what it was without reading anything, just thinking about it. And then I started reading the book and their definitions were more precise than what I had in my head. So frustrating. But, you know. That's my own fault for another reading and just thinking about things rather than what happens. I'm not familiar with the monitor behind you. I assumed this new. Oh, yeah, actually, we kind of moved. I'll give you a quick. No, I won't give you. Because I can't get the thing off. No, it's too tight. I'm sorry. No. Well, maybe I can do a little bit. You can go there. Yeah, like I can watch outside as well. This is the second floor. We built an office here. So I used to be in a living room, but that was kind of temporary, I guess. Then my parents moved in, and yeah, to the second floor. And the monitor is, it's, what do you call it? Like my parents moved house, so they had a bunch of TVs left over, and they no longer watch TV. So I told them like, oh, just give all the TVs to me. And I just plugged them all into the computer. So now I have like 4 monitors here, 3 of which are TVs. So yeah, that's what I did. In Agda, any text following also is considered a comment. Comments have no effect. Oh, we already saw this here, by the way, because I explained the paragraph they completely ignored. Like, it seems kind of important in inference rules, but they just like skimmed over it. But I expanded a little bit. So yeah, I mean, I thought this part was pretty important. In Agda, comments. Comments have no effect on the code, with the exception of special kind of comment called a pragma, which is enclosed between including the line, tells Agda n to correspond to natural numbers, and hence permitted to type 0 as shorthand for 0. Yeah, that's kind of nice. But this is a topology stream. No, topology will come later once we actually know how Agda works. And we're not going to do a topology, we're going to do a subsection of topology called homotopy, which has restrictions on topology. So like the full field of topology is really big, and apparently you can apply some restrictions to it to make it useful for figuring out equality between types. But that's later. We're gonna build a logic in types, basically, if we're successful with this book, which is a big if, by the way, because I hear many people struggle with it. So yeah, till now it's pretty easy. Probably gonna ramp up quite quickly. As well as enabling the above shorthand, the pragma enabled efficient internal representation of naturals using the Haskell type for arbitrary precision integers. The n with 0 and suc replaces proportional to n, whereas the representing it is an arbitrary integer in Haskell. Well, it's kind of shitty. You're replacing naturals with integers, but you know, do whatever you want, man. Okay, homotopy. Yeah, you don't know about homotopy? Yeah, you need to restrict it. Otherwise, I don't know why actually. I was just like, oh, I'm happy they're applying some restrictions. This is too difficult. Because what they're doing is they're kind of mixing up category theory with logic with homotopy. So those are 3 mathematical fields. You kind of have to know all of them to use this. No, it's category theory, type theory, and homotopy. So that's those 3 fields. Not even logic. Fuck logic. Yeah. Short, we will write some equations that hold terms involving natural numbers. To support doing so, we need definition, equality, and notations. The first... Oh shit. Okay, I guess we'll just add the imports. Maybe we should make a commit here. Already did, I think. Yeah. I think I should ignore that Agda file. Should ignore star.die, which is for interface. Okay. Just plug it in. We're not gonna read how this works because it's fucking boring. Well, maybe we need to read what these are. Okay, I'll just read it. The first line brings in library module equality and scope named ACK. The second line opens a module that adds it all in a name specified using open ACK using all the names specified in the using clause into the current scope. In this case, the names added are triple equals, I guess, equality operator, and REFL, the name for evidence that 2 terms are equal. Stands for reflection, by the way. The third line takes the module that specifies. It's nice that you don't explain what it stands for, but whatever. It's your language. The third line, this is strong equality, by the way. 3 equal signs. It's like really equal. Equivalence. So yeah, it's like in JavaScript basically. The third takes as a module that specifies operator to support reasoning about equivalence and adds the names specified using clause to the current scope. In this case, the names added are begin, takes a module that specifies operators to support reasoning. Wait, you import propositional equality as ACK. So this is a qualified import. And then you open the ACK qualified import to bring stuff into scope. Okay, we do that. We show how these are used. We've taken these as a given for now, but we will see how they're defined in the chapter equality, which is like a whiles away. I guess we just know how they work for now. Annoying. I guess you have to start somewhere, right? Agda uses the underbars to indicate where terms appear in infix operators. Are infix operators written between 2 I'll begin as prefix before a term. What the fuck? I don't know what this square thing is. I think it's like QED or something. Parentheses and semicolons are among the few characters that cannot appear in names, so we do not need extra spaces using a list. But this is a parenthesis! Click on it. I don't know what happened. Oh, here. What is this? Oh, I'm starting to panic. Oh, it's just a type class, I suppose. A module. It may be actually a type class, like an OCaml. Parenthesis, I think I'm gonna only do 1 chapter, by the way. A lot of text. Okay, I'm gonna do 1 chapter. I wonder, should I get a burger and get more swole or make something healthy? Swole? For something healthy, probably. Swoller. Oh. I don't know. I just do like I do like eggs for breakfast and then yogurt for lunch, and then, you know, dinner is whatever, and that means that 2 out of 3 meals of the day are already super healthy, so it doesn't really matter what you do after. White boy. I want to be the strong one. Now we have natural numbers. What can we do with them? For instance, we can define arithmetic operations such as addition and multiplication. Both. I wonder how you do subtraction if you have naturals only. I think you can do it with if you got bitwise. But this is not bitwise. This is the wrong encoding. This is not a good encoding for bitwise. So you cannot do the magic here. Yeah, I had yogurt and egg for breakfast and no lunch. Well, there you go. You don't read. Oh, I stand, man. This is also reading, and I'm standing, and I'm talking, and I'm socializing while I'm reading. Amazing. We're learning about natural numbers and recursive functions. Isn't that exciting? No, I presume it will heat up in the next chapter. Oh, we're actually gonna do proofs in the next chapter. Just the warming up. Yes. Oh, you know, you have to start somewhere. So, I mean, this is compared to the homotopy stuff, right? And it was just like the first sentence I read, I was like, what? What do you say? Homotopic book. Oh, I could understand, like, I think I could understand like the first page, maybe. Yeah, and there were like 300 more of those, 400 more of those. I think they were doing all of mathematics as well. Like, oh, this is how you do all of mathematics in homotopy. Don't worry about it. Define arithmetic operations such as addition and multiplication. As a child, I spent much time memorizing tables of addition and multiplication. At first, the rules seemed tricky, and I would often make mistakes. It came as a shock to me to discover recursion, a simple technique by which every one of the infinite possible instances of addition and multiplication can be specified in just a couple of lines. Here the definition of addition in Agda. What? If one side is 0, u are equal to n. What? If one side is suc m plus n, you are suc. Oh, you're just okay. You just oh. Why do you even need a better match on this one? I guess you need to remove the one. I don't jump back. Sorry. Operations on naturals are recursive functions. This is also kind of true in if you do it bitwise. We saw this. I think. Let's not get distracted, but I'm pretty sure that my bitwise definition was recursive. But that was because of the encoding. The encoding sucked. It was really slow. The first line signature specifying the type of is written and the bars arguments to go and names blah blah. First line type is specifying type of the operator indicates blah blah. Infix notation is shortened for applications. Why doesn't Agda mode respect color teams? Yeah, I don't know, man. I think it just does something. Who knows? The definition has a base case and inductive case corresponding to those natural numbers. Base case says that adding 0 to the number returns the number n. So if one side is 0, you don't care about what is you don't care about the 0, right? So you can like return the other side. Even if it's 0, it's just like, you know, if 0 plus 0, whatever, it's the right hand. And if it's 0 plus 1, you know, also the right hand. If it's 1 plus 0, this won't better match. You go to the next one. And then you go 1 plus 0. So that's the suck 0 will be 0 plus 0 with the suck outside. And then you go back here and you have the 0 and you get a 0 out. And then suck will be 0. It will be reduced to 0 because it's, you know, okay, I got it. I figured it out. Two examples just ran into my head, yes, and talked through it, but I don't know if I did it really. Anyway, so if you write 0, suck definitions 2 into equations. Okay, that is that. Meaning parentheses. Let's add 2 and 3. Gonna get an extra cheeseburger. Wow, that must be some really difficult work you're doing then. Well, I eat. Don't eat again. Get a second equation. We write equal for definition. We write for assertion. You already have the same. Definition is recursive. Also, the inductive definition, naturals apparently circulate on a problem. It works. Addition larger numbers is defined in terms of smaller numbers. Such definition is called well-founded. Inductive definitions of naturals, the apparent circularity is not a problem. Works because addition of larger numbers is defined in terms of smaller numbers. Such definition is called, for example, 3. We're just gonna step through it. But how does this work? Just you write 0 as 0 and sec m as 1 plus second addition push 2. Wait, what? Okay, let's just load it. No binding for 0. Because you need to have the natural. So that's what they said. We need to have built-in natural. Not in scope. What? Oh. Where did I get the n from? Well, maybe I have to do it after here. I think it worked. What's good motivation to have a cheeseburger? I don't know. I did the, what do you call it? The, wait, they're gonna show me tricks with only expanding shorthand is needed. How do I do these tricks with the editor? I think I can do this. So show me the magic. What are the spells? Wait, I'll just do full screen for a bit. Agda Refine. What do you think about that? You need to press the cursor on the go. On the goal. I don't know what a goal is. Begin. Okay. What is what else do we have? Previous goal. Show constraints. Like the infer type, maybe that sounds good. Do Control D. Control C, Control D. I don't know. Control C, Control D. Yes. Parse error. Oh no. Control C. Okay, wait. There's more. Rewrite. Y in scope. Bold type. S. Solve maybe all. Control C, Control S. Yes. Parse error. Oh no. It doesn't work. I wanted to do the magic. I wanted to do rewriting. Show constraint, show goals. Auto maybe all. There we go. It didn't work. What if we delete one? What if we delete another one? Ordered. Good job, man. I don't know what this does. What if I fuck up? What if I remove a suck? It's checking it. That's pretty cool. That doesn't suck at all. What if I suck here? It doesn't tell you at all where it is, but it is checking it. So what if I say 2 plus 2? What about the type? What if the type is not 5 but 4 and 2 plus 2? What about this? Oh my god! And we need to fix it all. We need to step through it. And it's jumping to where it thinks it should fix it as well. That's so cool. And just delete it. Delete it. Oh my god, why don't they tell you to use the editor more in the book? This is what I came for, Skybro. It's like, did you see that? Did you see that? We changed the type signature and it completely figured out where I should modify things for me. And we just modify it, we delete code, and it's working. That's pretty sick. I think it's really cool. So if the types don't align, you also get an error. Oh, that's bad because she should be here. This expression will never be true. Interesting. Oh, maybe if we keep it. Let's fix it first, and then we're gonna try and do some sucking. Suck up, come on. Suck up, come on. Suck, suck, suck. 4. Well, what if 4 now is 5? What will you do? So you're gonna say at the end you need to be 5, and now you don't know because it needs to be 4 as well. So you're jumping there again, and now you're saying, oh, it needs to be 5 as well. So you're jumping there again. Okay. So it's kind of like it always thinks the types are true and jumps to the terms, but no, they need to be both be true. But that's something to keep in mind, I guess. Pretty cool. Okay. Yeah, that's QAD. This is QAD. just like I suggested by reading. You got like begin and QAD. Oh, and there's no binding, by the way. There's no word here. We could give this a name. We could say like blah, because this is a function, right? But they were like, oh no, it shouldn't have a name. But we could give it a name. It's fine. Yeah. So this is just a function. And these are just terms. So these are, you know, hello world. We can do print here, print, blah blah blah. So this is just a program. And this is just a type signature. And we're just saying these things are equal to each other. We can do this multiplication in Haskell as well, by the way. We got it in naturals. We can do this equality thing as well, I think. Yeah, we can do all these things. This is still possible, this natural stuff. It it becomes a bit more difficult, but yes. I'm gonna get some. I'm gonna do a quick water break because I'm thirsty. I think I'm gonna get cool. I'll be right back in 5 minutes. Do I have a cool screen? No. Days. W starting. Good time to follow. No, we'll just do the beautiful lava lamp. That's the way to have a pause screen, I guess. I'll just give some tags. Okay. Quick coffee break. What do you want? We'll give you. Do we have latex? We have latex. Okay. Wait. Modify the text. There we go. Fika break. that's the way. Of course. Quick. And that's why you get the lava lamp as well. The lava screen, I guess. We'll be right back. Hey. Oh wait, you can see me. Guess I'm back. We go back. We continue. Here we back. The first line is the inductive case. Blah blah blah. Both derivations consist of a signature. Both derivations consist of a signature written with a column. Wait, what? The first line matches inductive case by matching m1 and 3. What? You mean this line? 0 and 3. The third line by taking n is 3. Where did you get these m and n from? Like, this text is more confusing than this code. I kind of instantly understood what this was, but it's not the first line. The first line is here, right? The begin 2 and 3, and you could say this is the first line because it's your type signature. And then, like, why don't you do the begin stuff in here, right? Why do you have to do it at term level? Why don't you do it at type level and just say term? Okay, whatever. Any question? Giving a term of a given type. Here we use a dummy name. The dummy name can be reused. It is convenient, for example. Names other than must only be used once in a module. I can't call a function named underscore, I suppose. I think in Haskell you can. It's just a function name in Haskell, but here it's like this is never going to be called name. Here type 3 plus 5 term provide evidence for the corresponding equations written in an entire chain of equations. Change starts with begin and finish. Pronounce QED. It is QED. I think it's the first thing I said, which is a guess, but yeah, it means so this is a abbreviation, QED. It's Latin for something. It's like QED. Of course, they won't explain you what it is. No. Quote erat demonstratus. So it's like as has been shown. It's the classical way of ending proofs. QED. Very frustrating to see because usually once you read a proof for the first time, you don't really. Well, I don't understand it. I have problems with proofs, which is why the proof assistant is here for me. This makes sense to me. This makes a lot less sense to me. I'm thinking too much like a programmer. In fact, both proofs are longer than needed. Agda is satisfied with the following. Raffle. I think this means we don't really care about terms. Just make sure the types are equal. Oh wow. It's still saying raffle is the thing that's wrong. But that's absurd, right? Because so we just said it's not equal, but it jumps to raffle. How much time does it take me to break Agda? Jesus, we're on the first chapter and I'm already. Yeah, I'm just not following the book. That's me, right? Do that. What I do, break things. In the change equation, all Agda checks is that each term simplifies to the same value. Oh, let's read this first. Agda knows how to compute the value 2 plus 3, and so it can easily check same as 5. A binary relation is said to be reflexive if every value relates to itself. Evidence that a value is equal to itself is written with raffle. But is it reflexive? I thought it stood for reflection. Wait. Nobody explains what raffle stands for. I thought it was reflection. Reflexive. Nobody knows. Well, there you have my. Maybe I'm wrong about that. We don't know. Duality of interpretation of that proposition. I mean, reflexivity is hardly equivalent. No, you usually do isomorphism. They don't do that either. Every value relates to itself. No, it's not at all what reflection is. Reflexive logic. I'm upset by Google for this stuff. But it's important to understand these things. Yeah, correctly. For any means that let R be a binary relation on a set X, which by definition is a subset of X. For any X and Y, the notation means that if X are X for every X, there's a relation to yourself. Oh, maybe that's kind of like isomorphism. Well, I said nothing then. What am I thinking of then? The other one, not. Small brain. At least my brain is smooth. Evidence that value equal to itself written as raffle. In a change of equations, all Agda checks is that each term simplifies to the same value. If we jumble the equations, omit lines, or add extraneous lines, it will be accepted. It stops us write equations in an order that makes sense here. Yeah, so I started deleting random lines and Agda was completely fine with that. So I guess this means there is a style to your proofs, and you can make them as hard to read as you want, which is an interesting thought, because perhaps the reason why proofs are so hard to read is not because of me, but because of the people that write them. How about that? Here 2 plus 3 is equal to 5's type, well, equivalent to 5, chain of equations. Also raffle are times for the given type. Alternatively, one can think of each term as evidence for this. This duality of interpretation times proposition and central to how we formalize the concept of Agda. It will be a running theme throughout this book. Note that when we use the word evidence, it's not quo focal. I have no idea what this means. Open to more than one interpretation. Okay. It is not like a testimony in a court, which the way that determined witness is trustworthy. Rather, it is ironclad. Well, we both know that's not quite true. The other word for evidence used interchangeably is proof. And I'm saying this is not quite true because it is true within the system you are proving, but these are so-called assumptions. Right? You assumed everyone already knew about natural numbers, therefore you could do this self-inductive relationship, which you did with proof by authority, right? You did it in the philosophy section, so you know there are assumptions in your proofs. And compute 3 plus 4, writing out the reasoning chain equation using the equations for. Oh, okay, let's do this. So let's do compute 3 plus 4. I don't know if this is allowed. We're gonna do it. 3 plus 4 is 7. So begin. Exercise. Practice. I mean, the really easy way of doing this is just saying here raffle, right? This will be true. But that's not what they're asking. Raffle. Oh no, raffle. What? It's a literal. Oh, we're not allowed to do that. Raffle? No, it's not a data constructor. Haskell is a data constructor. Here it's a function. Anyway, if we do this, and raffle will break. Cool. So at least our type is functioning, which is great to know. Then we can go on with begin. I guess we'll just dump in this. So here we do 3, 4, here we do 7. That's annoying. Does this load? Yes. So next one would be suck 2 plus 4. Can we do this? Yes, we can. And then we do. Oh, I think they did parentheses for because people may not know about fixicity. And the final one will be like this. Suck. Fixicity. Oh, you're putting it around both. Yes, we can do that. But that's different. Quite a bit different. So, I mean, the final thing we can do is just remove this. I mean, going back seems a bit redundant. So, yeah. I guess this makes sense. You just put in the exercise and then you put in the goal, and then you just fill up the space between to make it more readable. That's the overall strategy here. Maybe remove some parentheses here. Cool. Okay. Once we have defined addition, we can define multiplication as repeated addition. So what are we looking at here? The 0, we got annihilation. And here you are re-expressing multiplication through addition. So you're eating one of the ends. You have one of them, putting it in addition. Okay. Also note that this, let's actually put them below each other. I want to have comments. I have comments on this. Load. Like here you have 0 on the left side, 0 on the left side. And here you're returning the right side, but here you're returning the left side, right? This one also 0, but here you're returning the right side, like a mirroring going on. The recursive step is the same as well, but this operator is different. So there's like a lot of, I don't know, overlap. Looks like really similar to each other. I don't know if that makes sense to other people, but what I observed. I don't know what it's called. Probably has a name. I don't know it. Familiar equations. We get the first 0 times time. Yeah, I mean, yeah. I think this is how you got taught multiplication on elementary school, right? Just so you have 5 bicycles. You have 5 times 7 bicycles. So you know, 1 7 plus another 7 plus another 7 plus another 7 plus another 7, 5 times 7. Counting it out, that's what they're doing here as well. Okay, moving on. Rewriting turns the definition into 2 familiar equations. The first one follows because 0 times anything is 0. Second time because multiplication distributes over addition. In this general form, distribution of multiplication over division. 2 familiar equations. Well, they may be familiar to you. Well, annihilation, we just talked about. This one I just spent explaining. The first follows before 0, the second follows. In most general terms, distribution of multiplication and addition is written m plus right. Also, because high school mathematics, algebra, basic algebra. We call it algebra in high school. There you have it. We get the second equation from a third by taking m to be 1. N to be m, e to be n, and using the fact that one is identity of multiplication. Okay. Again, the definition is well founded that multiplication of large numbers is defined in terms of multiplication of small numbers. Of larger numbers defined in terms of small numbers. For example, let's multiply 2 and 3. The first line matches the inductive case. M is 1 and n is 3. What are you talking about? Is 1 and it's which m and n? Be this one? Yeah, it's this side. He's talking about this thing. First line m is 1 and n is 3. I guess he's talking about this line then. Second line matches the inductive case by taking m is 0 and n is 3. And you're just stepping through this definition, I guess. Okay, let's use the exercise. Compute using the equations for you don't need to step through the evaluation of plus. Okay. That's good. That would be a lot of work. Yeah, so let's compute 3 times 4. Compute mode 3, 4. I'm just giving things names because, you know, 2 bonus. So 3 times 4. Wonder how much that is. 8, 12. 3 times 4. We'll just delete everything in the middle. Oh. There we go. Right. So I mean, I guess we could just look at the example. You know, you take out 1 4, and then you do plus 2 4, and then you take out another 4 plus 1 times 4, and then you take out another 4. 4 times 4. We can say that's 0. And we can say that's 4 plus 0. Oh, I broke it. No. Oh, that's syntax error. Yeah. It's a syntax error. It doesn't like that. It doesn't like that at all. I wonder how they like if you've never done any Haskell, how would you deal with this kind of stuff? Because it's immediately obvious to me what's happening here, but like, you know, this is perfectly valid math, I guess. Even like this is perfectly valid math, but you may not realize you have to add these stupid brackets because it doesn't have the fixicity rules. Yes. I don't know if you can get away with it in Haskell either, but fixicity rules. Okay, moving on. Exercise. Turnstile. Define a moral exponentation, which is given by the following equations. Ooh, this is a real exercise. So here we need to define this thing, I guess. So what if I mean, you know, do you really think this is also 0? We just follow the observation I just had by swapping out these functions. I think they will work, but we can try it. We can, you know, we can just like experiment with this, right? So 2 to the power of 3 is 2 times 2 times 2. So that's 4, 8. Compute power. I guess we lied. Ooh, we fucked up. Let's do the base case first. I think it should be 0, but we can check it out. So if you do 0 to the power of 4. Oh, wait a minute. This is another base case. M to the power of 0 is equal to 1. So that's flipped, right? 0 to times n. Why? I remember that. So m to the power of 0 is equal to 1. And then, oh, this matches up. Oh, that's pretty. That's so cool. Ooh. What? Why is this the other way around? And again, what's happening? Oh, single. It'll suck. Just suck once. 2 to the power of 3 to the power of 4 is 80. What? We just encoded these rules. M to n times m. Both. There, we did it. So, do I need to write out the proof as well, or can you just do raffle? I guess we should write out the proof. Proof by intimidation is my favorite. So, but they really look like each other, the functions. Like, they have a lot in common. I mean, I guess they're both, well, you know, there's not that many possibilities, but, you know, it's different. I don't know. I thought I saw something. I don't. Proof by intimidation is my favorite. Proof by intimidation is the only. The logic teacher used to do this because, like, some concepts it's just too difficult to grok in one go, so you have to like sort of just hand wave something at first before you can come back later and do it right. But they are doing this here as well because they're not saying how this equality stuff is working, skipping it, saying like, oh, just believe in us. But I guess they're telling us to have like proper proof form and don't use raffle. So we are actually gonna write this out as well. Okay, yeah. I'm a good boy. Yeah, it's goodly. 3 to the 4th. Begin. Zoe. We will delete bodies. Delete all the bodies. Give me my own one as well. 3 to 2 is 3 times 3 is 9. What? Oh wait. It's because of the binding. I don't even read the error message. I guess the programs are too small to have to care about them. So here we step to the other side, right? So here you have to do you reduce from there 1, and then you're doing times 3. Oh, this makes sense. Then you're doing another reduce, and you're doing another times 3. And you're doing another reduce here, and you're doing another times 3. I mean, you're gonna get a massive parse error again, but I have a trick up my sleeve for that. Times 0, which will give us the base case. 1, and we have to be 1 because otherwise math annihilates. Okay, cool. So I may have lied about it, by the way. It's just gonna be. I realized my trick doesn't really work. So we're just gonna add the parentheses wherever. Oh. There we go. We wrote it out. We did our homework. We now know how. Actually, this is a pretty nice way of learning how this shit works. Because you're mechanically writing out the entire thinking step by step. And I wish I had this stuff when I was in high school, but I didn't. So, land of Lisp, yeah. This is it's a good thinking tool, really mechanical. I see why they like it. Because, you know, this is how you learned how the power works. I mean, this is how I learned it. So, you know, it's just this indicates how many multiplications are there on this side with itself. Bonus. We can also define subtraction. Since there's no negative natural number, we subtract from larger numbers from small numbers. We'll take the result to be 0. Yeah, so we did the recommended exercise. I'm gonna give myself a pat on the back. And I'm gonna make a commit. exercise. Good job. We can also define subtraction. Since there's no negative natural numbers, we subtract larger numbers from smaller numbers, it will take a result to be 0. This addition of subtraction to naturals is called monas, twist to minus. Wait, what? Since there's no negative natural numbers, if you subtract a larger number from a smaller number, you will take the result to be 0. So you truncate on 0. Okay, cool. It's called monas, which is different from overflow. So I guess you have like subtraction with a minimum of 0. Okay, this is a combination of subtraction and then you compose it with minimum 0. Okay, cool. Monas is the first use of a definition that uses pattern matching against both arguments. Oh my god. And pattern matching they do. Land of Lisp. Lisp is love, life, absolute madness. I'm having fun with this book. What do you say about that? Like, in the beginning it was a little boring, but now it's getting more interesting. Because I had to do an exercise which was somewhat challenging. It wasn't like obvious. Well, it wasn't. Yeah, it wasn't obvious. I had to have a think. Beginning there was boring. Yeah. And there was obvious. And then power came, which gave me a thunk. Yeah. Okay. If you subtract something with 0, you return the result, obviously. If you subtract 0 from something else, it means you're going below 0, so you should give 0 according to the definition. And if you subtract 1 from another one, I guess we're stripping the ones and calling ourselves again. Okay. Oh, you're continuing doing subtraction on both sides until you're reaching the base case. One of the base cases. So you're either reaching 0, where the left one has no longer anything inside of it, or you're reaching the other base case, which means you're going to return what's happening on the left side. So this definition is also a bit different from also different from the other one because why? Yeah, it's no longer it no longer looks like a mirror image, and it doesn't commute like the other ones do. So we put them all below each other. You can see what I mean. Like this sort of looks like this. If you say this is a function as well, like here, it looks like each other, right? This then also looks like this, like a lot like this, except the argument is a little bit different here as well. This does not look at all like this. It's completely different. You have multiple patterns, and pattern matching is different because on both sides, and yeah, I guess the base case is the most similar here. Yeah, that's what I think of it. Different. And also associativity, my final argument that this is actually a really different thing. Some music to help you think. Why did you put a timestamp in? So maybe we can play music. Land of the Lisp. No, we're not gonna play that intro. We're not gonna play that too often. Again, the recursive definition is well founded because bonus on bigger numbers is defined in terms. Oh yeah, we're blah, blah, blah. Bonus on bigger numbers is defined in terms of bonus on small numbers. I don't know what they mean. They keep on bringing this up, but I think it behaves the same for the bigness and for the smallness. So you might as well do it recursively. There's no need for having a separate definition for bigness, smallness. But yeah, that seems so because the entire construct is built around. Well, they call it induction, but it's basically the same thing as recursion. Like it's an inductive definition, therefore it makes a lot of sense to use recursion. All behaves the same. Anyway, we'll just compile. There. Example, let's subtract 2 from 3. We didn't use the second equation at all, but it will be required if we try this from a smaller one. Yeah. Exercise. Writing your reasoning as a chain of equations. So they're saying that we should use the chain of equations. Did I do that here as well? No, let's just check that. So I guess we did too much work for the... Okay, we can do this. Yeah, I think I'm gonna stop giving it names now. It's getting annoying. Yeah, so that's monas, which we need to copy as well, because I can't write this stuff. Thanks for not explaining how to, by the way, but our copy trick will work. Okay. 5 minus 3, 2. So copy over this term level. Did they explain the difference between types and terms at all? I wonder. Probably not. What do they do? Oh, I see what they're doing. It's just 4 minus 2. 3 minus 2. Oh, okay. 3 minus 1. Well, I guess that's it. Well, that's dumb. Well, that's easy as well, I guess. We didn't have to think. Well, we had a little think in the beginning, a little funk. And then we prevailed again. By quickly looking at the examples, we figured out what we had to do. It turned out to be quite easy. And then we did the thing. Congratulations, everyone. It's still quite easy. So, yeah, you know, we're just gonna go to 0. There we go. Fine, I'll play it myself. Isn't that common knowledge? What is common knowledge? I wasn't paying attention to chat. You can play it yourself, man. That's why I'm not playing music right now. So you can have your own favorite music. In real life, I think it really helps with people around. What if I don't want people around? Type level and term level. Isn't that common knowledge? It's actually like you should talk to some Python or JavaScript programmers. It depends on the one, like once you're talking to as well. What are they? Like, I mean, they just feel like it's getting in your way and slowing you down, the type system at all. But something like this, where you do the computation at type level, that's just like, you know, would ask you, why would you even do that? The point. Good question. It's because they only use the band type system, like the one from Haskell. Have you ever done doing this stuff in Haskell? Yes. Okay, precedence. It's kind of funny. They put the analogy in of story of creation, but then they're using it for Platonic idealism of numbers, which is basically something completely invented by humans and doesn't, like, some philosophers argue that numbers don't exist, you know. So they're using the story of creation for something which, like, a sizable chunk of people believe don't exist. Don't you see the irony here in this book? Maybe they did it on purpose, you know, just to troll. They used a bad type system. Well, I think they just never had the value of a type system occur to them, only getting in their own way. But the point is, it also gets in your colleagues' way, and they have to deal with your type level shit. Allows you to make stuff that... Okay, whatever, I'm not going to talk about it. We often use precedence to avoid writing too many parentheses. Application binds more tightly than, or has precedence over, any operator. So we may write means suck. Multiplication binds more tightly than addition. There are good reasons for that as well. Because... Wait, I think there were good reasons for it. No, they're not. That's arbitrary. Okay, cool. To mean blah blah blah. We also sometimes say that addition associates to the left, meaning M and P. In Agda, precedence and associativity of effects need to be declared. Oh, cool. Please remove the types before giving code to your coworkers. Who did that? Oh, yeah, right. A colleague of mine. Oh, I think he's leaving as well. Yeah, he cleans up the type signatures and then it's like, oh, then I can have more code on screen and have it more tightly together. It's like, yeah, you're not wrong, I guess. Not wrong at all. I mean, look at the beauty defining here. It's jammed on this side. Like, this is like a fourth of my screen. So there are two more, or I guess three more of these screens next to it. And I just put empty terminals there to push it here. And I have one more monitor there and one more monitor there. That one shows OBS, and that one, well, Discord, I'm not really doing anything with it right now. But yeah, so this is like quite tight screen for this. But it doesn't matter because the proofs are so small. So this states operators plus and minus have precedence on level 6, and operator R has precedence on level 7. Nothing with multiplication because they have low precedence. So now we should be able to... Yes! Oh my god! Because it figures it out. It did something. And now it's no longer a parse error. Oh, it didn't... I think we forgot to do the roof, which is actually more tight than multiplication. Oh, because it's an exercise. They're not sure if we actually did that. We did. We have chosen to represent function of two arguments in terms of function. First argument represents second function. Second argument. This trick wait, what? We have chosen to represent a function, two arguments in terms of a function. First argument that returns a function of the second argument. This trick goes by the name of currying. Agda, like other functional languages such as Haskell and ML, is designed to make currying easy to use. Function arrows associate to the right and application associate to the left. Currying stands for hands up against 5. Currying is named Haskell Curry after when the program that has also named. Curry work dates to the 1930s. When I first learned about currying, I was told it was misattributed since the same idea was previously proposed by Mas Schronkel in the 1920s. I was told a joke. It should have been called Schronkflickling, but currying stays here. Only later did I learn that the explanation of the misattribution was itself a misattribution. The idea actually appears. What? Goto Fridge. So we should call it Fridging, I guess. Now Skybro, you go look up the paper from 1879. Actually should do that. Because you can see how fucked up history is. Like the paper and shit will be yellowish and disgusting to read. So great to look up. Yeah, it's like actually difficult to find these kind of things. We're gonna fact check this guy. Because there's a fat chance he is misattributing himself as well. Anyway, well, one of the problems with this misattribution stuff is that the lambda calculus itself is, I'm not sure how old it is, but I'm pretty sure lambda calculus comes from the 1990s. So one wonders what this guy proposed and old stuff. I care about my history, okay? The story of creation revisitors. Just as the inductive definition defines naturals in terms of naturals, so does a recursive definition define addition in terms of addition. Again, it is possible to assign definition a meaning without resorting to unpermitted circularities. We do so by reducing our definition to equivalent inference rules for judgments about equality. What? 0 plus n. N. You need to have an n. And then you have 0 plus n. So let's go back to our inference rules, which I said this may be important, and now it's coming back. So we had a judgment and a conclusion. This is our judgment. Judgment is our conclusion. So they are now basically putting the function definition in here. Here we assume we already have defined terms in infinite set of natural numbers, specifying the meaning of the judgment, and to the first inference rule is the base case, natural number, then adding it to 0 gives n. The second inference rule is inductive case. First adding m and n gives p. Fuck m. I don't know what they're talking about here. They're not doing a pattern match. Doing a pattern match in a conclusion. No sense to me. There's no recursive step. Pretty sure what they're doing. Specifying the meaning of the judgment. First inference rule is the base case. It asserts that if n is a natural number, and adding 0 gives n. The second inference rule is an inductive case. It asserts that if adding m and n gives p, then adding suck p sucks. Again, we resort to creation story where concerned with judgment about addition. In the beginning, we know nothing about addition. Now we apply the rules to all judgment we know about. Is this like some kind of theory stuff? The inductive case tells us, or maybe this is the theory part, like the programming language theory. This is how they're doing it theoretically. Okay. We didn't know any equations about addition before today, so that the rule doesn't give us any new equations. Then we repeat the process. Yeah, in your ironic number definition that is potentially not real, because nobody believes numbers are real. Well, some people do. Maybe like most people don't really think about that. Where do you see your numbers in the nature, right? Where are your ones in the trees and fives on the road? I guess in Dutch the word for pond, the word for a pond looks kind of like 5. So that's your 5 in nature. A wild 5 appeared. Then we repeat the process. So next day we know about the equations from the day before. No, all the equations where the first number is less than m. 0 and 1, additions of 0. We can see the reasoning that justifies inductive and recursive definitions is quite familiar. Same side of the coin. What? The above story was told in a stratified way. First we create an infinite set of naturals. Then we take given the creating instance of addition. So even on a day 1 we have an infinite set of instances. Instead we could choose create both naturals and instances of addition at the same time. Then on any day we would have an infinite set of instances. Now we apply all the rules of judgment we know about, giving us the new naturals. I have no idea what they're talking about. 0, all sums that yield 0. You've got the hang of it by now. I guess. Oh, well, actually, this is more pragmatic. Only n state will be distinct natural numbers. This gives an entirely finite view of finite set of data equation relating data. Does anyone know what this means? Like, these just seem words about what? This entire chapter should be deleted. This again is super pragmatic because the question mark indicates you would like fill in a part of the code. Oh, yes, I would like that, Agda. Begin by typing blah. You can do that. Question mark indicates you would like Agda to fill a part of the code. If you type Ctrl+C, pressing Ctrl key while hitting C, followed by L key, which stands for load question mark placed. The empty braces are called a hole, and 0 is the number used for referring to the hole. The hole will display highlighted green. What? What is this? This is what I was talking about, Skybro. This is the magic of tactics. This is the presentation that what's it called? Sandy McGuire was giving in Haskell to introduce tactics-based programming. This is already part of Agda, I believe. Sandy, yeah, Sandy. So here they're gonna give us ways to solve the constraint. I guess the empty braces are called hole. The hole display highlighted green. You may want to create a window displaying text. N indicate hole n is filled with the term n. Typing Ctrl+C, Ctrl+F will move you into the next hole. Ctrl+C, Ctrl+F. We wish to define addition by recursion in the first argument. Move your cursor into the hole and type PC for case. You will give him the prompt. This is the case splitting. Type m will cause the split on that variable. M. What? This is magic! Oh my god, this is so cool. This is Sandy's thing, right? He made it in Haskell. It already existed in Agda before. So cool. Wingman! Yeah, but unfortunately Wingman is impossible to use. There are now 2 holes. And the window at the bottom tells you to require a type of each. They both need to be n. Natural. Going into hole 0 and will display information. So we can go Ctrl+C, Ctrl+F, and then we can do Ctrl+C, comma, goal n. And what variables available? Goal n. N. This strongly suggests filling the hole with n. After the hole you can type, how do I fill it? How do I fill the hole? Wait, how do I fill the hole? Impossible? Forward. We wish to addition and recursion first argument. For case, maybe case. Question to give. And that worked. Ctrl+C, Ctrl+F. Okay, we're going to the next one. I don't know what I did. I pressed Ctrl+C, Ctrl+space, and then was expression to give, and I said n, and it worked. So I think we can just edit it in Vim as well. We can just ignore this entire mode and say like, oh whatever. But yeah, this is pretty cool. Again, going to hole, type Ctrl+C, Ctrl, comma, will display information as required, type of the hole, and what 3 variables are available. Ctrl+C, comma, n and m. Here, n and m are available. Going to the hole and type, will fill the constructor. Do you need choice? I'll tell you who constructor to might use. There's a choice, in this case, it will display the following. Ctrl+R. I don't know which constructor introduce 0 or suck. Filling the hole with suck by Ctrl+space, suck. No. Oh, Ctrl+C, Ctrl+space. I need to do suck question mark because I need to put in the hole, right? I will give the following. So you need to do exactly what they're saying, kind of. Not in that case. So filling the hole with suck, typing Ctrl+C will split in the following. Going to the new hole, give you similar definition. So we need to do Ctrl+C, Ctrl+F, Ctrl+C, comma, Ctrl+C, Ctrl, comma. So the goal is n and m, and they have a bunch of constraints as well. We can fill the hole with m plus by Ctrl+C, Ctrl+space. So we're writing it out again. C space m plus n. But it's putting the parentheses automatically around it, so that's pretty cool. Exploiting interaction to this degree is probably not helpful for a program this simple, but the same techniques can be helpful with more complex program, even if the program is this simple. Using Ctrl+C, Ctrl+C to split cases can be helpful. Yeah, I know, I saw it on the AST of Haskell. Like he did it on the entire syntax tree of oh my god, I have so many ideas now about it. I'm gonna talk about it in a moment, but yeah, he did it on the like template Haskell's AST, which is massive. That's like 30 or 40 sums, right? And he's just like automatically generating a case split on an entire thing. It would be a pain in the ass to do by hand, but he just did it in like a second or so. That's pretty great. That makes me envious. Right, and the other idea I had was like, okay, you know, the other way of splitting is by using prisms, because you can create morphisms if you fold over a prism pattern match. That would be pretty interesting as well, but that's a crazy idea. Probably another PhD idea. Okay, this stream has been surprisingly exciting. I thought, yeah, yeah. I'm impressed. I'm impressed. More pragmas. Else? Library. Here you go. Okay, good. We can go through this. Including the lines tells Agda that these operators correspond to the usual ones, and enables them to perform these computations using the corresponding Haskell operators in arbitrary precision integer type, representing naturals, zero sub. Yeah, so Haskell is the underlying language, and they're using the Haskell stuff for speeds. Quite clever, because PHP is like, there's just no way you're gonna be competitive with UHC. You're upstarting a language. So, great idea. Haskell requires a proportional sum algorithm. Exercise, bin, stretch. A more efficient representation of natural numbers uses a binary rather than a unary system. We represent numbers as a bit string. Oh, I want to do this. Net plus integers in Haskell requires time proportional to the large logarithms of m and n. Currently representing naturals in zero sec requires time proportional product of m and n, whereas representing natural integers in Haskell requires time proportional to the sum logarithms of m and n. So they're explaining type complexity differences by using the Agda representation and Haskell representation. Basically, Haskell is faster. I guess that's why you would do this. Okay, cool. Maybe can I just dump it in here? Or I need to do it below the definitions. So. Yeah, that's the other thing, right? In Haskell, you the module, like there's no, it doesn't matter where you define things. That's actually that's something difficult. Not a lot of languages do that, but in Haskell, it doesn't really matter if you put the power there or if you put it above it. But here in Agda, it will break. So it's basically like you need to put definitions below where they come in the program, and that's something to keep in mind. I guess Haskell makes that easier for the programmer, at least. Like you can just dump it wherever. But in Agda, it matters. Oh yeah, it's quite opinionated. That's like another thing, you know. I instantly realized what's happening because I use PHP so much. So that's the same issue in PHP. I was like, oh, of course, it's like you need to do it in order. But, you know, if you don't jump languages a lot, then this may not make a lot of sense to you, I guess. Right. So a more efficient representation of natural numbers is using a binary rather unary system. Represent numbers as a bit string, for instance, a string ending for number 11 encoded as blah. And 11 is also represented by find a function inc that converts a bit string to the bit string on the next higher number. We could do that. Confirms encoding 0 through 4 into bin. Well, you can just hard code this if you wanted to, but that's not what we're gonna do. Bin to bin. We got a pattern match on this, don't we? So what if it's unit? I guess your unit. Wait, is this how you? Unvalid expression. Oh, this is not unit. This is something else. Like this. So the x gets before what? So the final thing is unit. So that's the end. So that's fine. I get well, if I get that one should become. We need to read the next one. Oh no, this one is difficult. I guess you need to go all the way to the end. It converts a bit string to the bit string in the next higher number. But 100. I need to know the previous one. I guess we can do is O. We have booleans. Bin. What? Well, the most shitty way of doing this would be like you just write all the patterns, right? So O. What? Oh, right. The underscores are not right. So you got O and you got I. So if you are at the end and you have an O, you should be a 1. And if you're at the end and you have a 1, you should be an O. But there is something else. Because in this case, you need to carry. We need to increase the one before you as well. I guess you just do like before. No, that's not what I... Oh wait, we're going from left to right, right? So, and you want to increase it. Hi bro, small brain. We're going left to right. You want to increase it. So if you encounter a 1, you want to increase it by 1. Keep yourself. This is pattern matching on the right. I thought this O would be on the end here. But it's not. We're pattern, in this case, we're pattern matching here. Hey. I need to split it, I feel. Because if I have a memory of whatever came before, then I can do it, right? No. No. I know the base case. That's this. No. If you have, we can do it. We can do this in code completely. We can do it like this. It becomes. Right? If you just jam O behind it and an I in front of it, and then anything else is just no wait, but not. It's the wrong. It's the wrong way around. Need to be uniform at the end. Countering some, so you increase it to maybe. Inc pref. Next. I'm encountering some high. Maybe I should just increase it. This doesn't seem right at all. Even that gives from 0 to 4. This is like very similar to what we did with our processor. And it's an exercise in here. Isn't that cool? But this is complete. I'll prove it. 0, 0, 0. Proof inc 0. Proof inc 0 is equal to y. Not. Oh, of course not. Okay, that's correct. Proof inc 1 is equal to 0. Okay, proof inc. So I'm going from 1 to this. Not. Could not parse. Oh. Wait, what? And then the final step is to do inc II should be I 0 0. 0 through 4. 0 1 2 0 to 1 2 to 3 3 to 4. Almost. Only one case is failing. So this is if we put in 0. So what are we patching matching on? We're patching matching on the empty list. Oh, no. Wait, what? How are we going through this even? Well, you can't even do anything. So, no, we're going from right to left, I think. So, you first pattern matching on 0, which you will turn into a 1. And then you're going to the next one. You shouldn't increase the next, because you already have increased the next. So, yeah. Okay, let's fix the test one. And then inc I is not equal to IO. Why are you IO? Well, like this. What are you returning? This doesn't seem right either. Because we're putting, what is it returning? I think we can use the step trick to verify this better. Yeah, do that. The worst of ideas. Inc. This is the goal. Delete the body. I think it's a good idea to just write out the cases. You don't really understand what's going wrong. So in this case, what would happen if we go one step deeper? We're adding this at the end. We're snooping off this one. and we're going forward, and then we're having another I. So the same thing happens. This is where it's going wrong. Pattern is wrong. This just eliminates this. So all of this stuff is true, which means our pattern match is misbehaving. You are at the end. You're encountering you need to be 0. Don't increase the next. Okay, why are you misbehaving? You're now succeeding. Okay, cool. Now let's step through this one and see why this one is failing. Okay, I'm getting it. I'm getting how to solve these problems. Like we're having a way of incrementally figuring out how our code is trash, which is great because all of code is trash. They basically taught us how to do this. So I mean, this is also interesting to me. Oh my god. I think this is super interesting. So what happens if you do this? Think next, but if it's unit. So I guess there's a special case because what's gonna happen for this one is gonna be I. Unit I. And it's failing on that. Wait. Next. Oh, it's gonna be. Wait, what? What? Begin. Inc I. So you're gonna. Oh right, you're gonna return. You're gonna return 0 from this application. Yeah, 0, which is an O. And then you're gonna do this. What? Which is gonna be unit. So our problem is that we need to pattern match on this specific case because yeah, we can't quite do this. We need to I need to introduce another. Right, now this no longer is valid because the definition is changed. So it's gonna be this, and you are this. And then you break. Oh, it never gets any easier. Yeah, so we can delete this. I think we need that case of. No, this is not right either. This is only for the base case. We should only flip a 0 to a 1 for the base case. Otherwise, you're increasing too much. So this fixed the 3 to 4, but now 2 to 3 is broken again. I guess we'll step through this one as well. See why this is broken. What? Did I fuck up my encoding or something? 11. Oh, let's see. You're gonna go to 0. Oh, that's not right. This is the opposite of what I want. God damn it. Next. I don't want that because the. Wait, let's just put it in the graph again. Are you upset? Oh, I wrote this wrong, I think. Intentionally. One. Do it again. I have to close. Okay, so the first thing you're matching on is a 0. You're flipping that to a 0. You're saying to increase the next. And then you're pattern matching on the end of the string and I. You're emitting an I and a 0. This would mean you're this. And that's the same as saying this. And this completes our entire proof. Our program is correct by these proofs. It converts a bit string to a bit string to the next higher number. For example, 12, 11. We try out 11. I don't know if this is gonna work. Probably not. I'm not sure if I'm gonna solve it either. Damn it. I'm feeling like time constraint is an issue now. We should have that. We should have this indeed. Damn it! Oh, wait. Oh, wait, I'm fucking it up. I'm fucking it up so bad. It's working! Oh my god, it's working! Wow. Okay. And then the final thing, leading zeros. Leading zeros. How would you deal with that? Good question. What do you expect out of it? Probably this will be fine. That's also working! Oh my god! Skybro, are you watching this? We did a thing. We didn't even think about things. We just like did stuff in the assistant, and now we know it works. It's like, it's so much easier than the type level bullshit. Like, we can actually step through things and assure that it's working correctly. Did you know how much issues we had with it fucking the type level processor was such a fucking pain in the ass. Oh my god. Oh my god. Oh my god. Agda is so much easier, Skybro. Oh, I've experienced pain. All of the it's like nothing compared to Nix or that type level bullshit. I don't know. Maybe it's gonna get higher. We don't know. Like, the book seems, I don't know. It's the first chapter. We shouldn't get overexcited. But this is very doable. All of this stuff. It's fun. It's doable and fun. Kind of like it. That's it, Skybro. I'm gonna marry Agda. I've decided. At the end of the chapter, we'll show how to find relevant definitions in the standard library, the naturals constructor for them, and each of the operations defined in the standard library module title.net. Formally, we'll show an import running code, so Agda will complain attempt import definition that is available. This time, however, we have only shown the import as a comment. That's okay, cool. So I'm just like adding comments to say someone else wants to look at it or whatever. I doubt anyone will. Yeah. I haven't had so much fun programming in a long time. At the end of the chapter, we'll show find relevant definitions, and the book is also fun to comment on. It's like really it's like it goes all over the place, which is fun for me. So like, oh, are you sure about this? Oh, are you sure about that? So yeah, but makes it good for me to read. Normally we'll show import as running code, so Agda will complain if we attempt import of a definition that's not available. This time, however, we have only shown the import as a comment. Both this chapter and the standard library invoke natural pragma, and lateral equivalent to data.net. And such a pragma can only be invoked once, and as invoking twice will raise confusion, where 2 is the value of n of data.net. Similar confusion arises if other pragmas invoked. For this reason, we will usually avoid pragmas in the future. Information on pragmas can be found in blah. I don't know what a pragma is. Wait, what? At the end of each chapter, we will show you where to find the definitions for that library. The naturals constructor for them and the basic operators upon them are defined in the library module data.net. Normally, we will show import as running code, so Agda will complain if we attempt to import a definition that's not available. This time, however, we will show the import as a comment. Both this chapter and the standard library invoke natural pragma. Natural pragma. Nyaruguro. Well, maybe you shouldn't have invoked it in the standard library then. Okay, so you can only use the natural pragma once. Otherwise, you angry at Unicode. This chapter uses the following Unicode. Double stack capital N. Each line consists of Unicode capital N, corresponding combined to the name of the character. Type to generate it. The command R gives access to wide variety of arrows. Does that don't work? R. After typing R, one can access many available arrows, right, up, down, navigate. The commands member where you navigated works. You write CB to stand for Control B. Similar. No goals and log. What? Agda show translation. Input just evil. Oh, I guess I can just search for it in the buffer. So I'll just do and then what I do. I mean, the Unicode isn't handy at all. But I just write the latex command. That would be more convenient, I guess. Copy pasting has worked great until so far. So quill show key. Each line consists of a Unicode character. Name of the character. The command R gives a wide variety of arrows. Typing R. Where do I? All characters supported by Agda mode as shown. We write MX for typing. We want to now input a specific Unicode character in the Agda file. Move the cursor into the character. Will show queen. Oh, let's see. That's wait. Will show key. This is the thing you need. Type. So the. Oh, I can just type the LaTeX. Oh, that's so convenient. Can you do like two? You can even do the logic stuff. So you can do like intersect. No, I guess I forgot how to do it then. We can do like a wedge. That's oh, that's so cool. Are you seeing this? Oh my god. Union. No, union. That's union. And you got like a cap. Got a thing. But you can also get like a leg less than equal neg negation. That's so cool. You can just put. What is the problem? Oh my god. So we finished the cap chapter, and I'm interested in this, but I'm gonna end the stream here because I've been doing this for 3 hours. That's actually like one of my longer streams, I suppose. But it has been amazing, and I'm definitely gonna continue this because it's like so much fun. So yeah, I'll be back next. I don't know. I want to say tomorrow, but I probably don't have time. So yeah, but I'll be streaming this again because this is so cool. Thanks for watching, everyone, and see y'all later. Probably in the weekend or next week. Bye bye.